This is the worksheet on applications of antidifferentiation. I think the focus of this one is going to be on your ability to use the CAS calculator effectively. So I am going through every question using the CAS here. You want to save as much time as possible. Question 1 is looking at velocity. We did this in class, so I'm just going to go through it again with the CAS. The velocity of a particle, v meter per second, at time t second. So take note of any condition. So in this case, the domain, obviously time has to be positive. The other thing that you want to pay attention to is the unit for velocity. In this case, meter per second, which means that if you go up to position, it will be meter, and if you go down, will be meter per second or meter per second square. This is the equation for velocity. So I'm going to start by, first thing I'm going to do, it's not that, I'm going to write it in the CAS here, is I'm going to define velocity in terms of t. So that's the first thing I'm going to do, and I'm going to go define v of t. I don't think we need to sketch at any point for this question, so it doesn't matter if I use t as my variable. You just need to keep it consistently as t. So define v of t as 3 times t squared minus 8 times t plus 5. It's done. So I've defined my velocity. It is initially 4 meter to the right of a point not 0. So this is the information regarding the position of the particle at the starting point. So when time is 0, the position is 4 to the right. Another thing that it's probably going to be quite useful to do is to remember that. So when time equals to 0, let's just translate that here. What this means? This means that when time equals to 0, when t equals to 0, position is 4. Okay. Particle starts from rest. Part A asks you to find the position and acceleration at any time t. This is another way of asking you to find an equation for a position and for acceleration. So first of all, I'm going to define position as p of t. Okay, and the position can be found from anti-differentiating velocity. So define p of t as, and to find the antiderivative, I'm going to go to that box next to the little book. Hopefully you're looking at the left side of the screen, and you are selecting this one that doesn't have a little box on top or bottom. So we're looking at this, and it will come out. Can I even, anyway, we'll see what's happening here. We're going to have v of t. An important thing to note is that if you are using t as the variable, then this has to be anti-differentiated in terms of t, not x. So that's that. Now, if I'm typing p of t now, I think I need to zoom. Okay. Hopefully you can still see. This is not great. Maybe I should change. No, I think this is still a little bit better. Okay. I was thinking. No, we're going to stick with it. If I'm writing p of t now, this is... Ooh, what's going on? Okay, so see there is a mistake here because I have defined v of t incorrectly. This is a very easy thing to fix. It's supposed to say my plus, actually. So that, because I still define my p correctly, so now I have p of t. Another issue with using anti-differentiation in the CAS is that it doesn't actually add c next to it. So you might have to redefine. If you want to do everything in the CAS, well, you don't actually have to redefine. Equals to, let's go with that, and then I'm going to add plus c next to it. Okay, you know that when t equals to 0, the position is 4. So p of 0 equals to 4, and you're finding c, so c equals to 4. And just to make things easier, I'm going to redefine p of t for the last time, but now adding 4 as c. So check. There you go. So this is my position. well, not my position, the position of the particle in terms of t. For acceleration, which is the second part, you just need to differentiate velocity. So I'm going to define acceleration as a of t. Okay, and a of t equals to, you can go to the same place to get ddx of v of x. See, I've almost made a mistake here. It needs to be ddt again, since t is the variable. And to get the answer, this is going to be acceleration in terms of t. So answer to part A is just p of t equals to that. This is the first answer. And a of t equals to that is the second answer. Next, you need to find the position when velocity is 0. So to find the position when velocity is 0, you first of all need to find time when velocity is 0. So I'm going to solve. Let's just write out what I want to do. So I need to find t when velocity is 0, then sub these t values in the position equation. Okay, so we need to solve v of t equals to 0. Solving for t, you have two answers, 1 and 5/3. They are both positive, and I don't think there is any indication anywhere that there is any other restriction on time, so I'm going to use both. If I have p of 1, that's 6, p of 5/3, just get the fraction out. 5/3 is 158/27. So there are two positions when velocity equals to 0, when p equal to 6 meter, or 158/27 meter. Lastly, you need to find the acceleration when velocity is 0. Because there are two t values at which the velocity is 0, I need to find two acceleration. That does not look good. And the other one is still 5/3. And that's -2 or 2. So that is the end of question 1 using the cast for every part.